Thank Professor Patnaik and his colleagues for giving me this opportunity to come here to a familiar place. I start before they start showing the slides that I'm speaking from a vantage point. Am I audible to the audience? Yeah. Speaking from a vantage point because graphene has been discussed by several speakers. Arindam Ghosh talked about it in the first lecture. Bhaskaran alluded to it. So did Jayendra Jain. And just now we heard a very comprehensive, very extensive study of graphene. And a Dada of graphene theory is also sitting here, Amit Agarwal. So I start speaking with some trepidation, and fortunately, I'll be brief in the introductory part because Amit noticed has a Dirac-like structure, which also shows up in graphene that was presented already by Ovik, and other speakers as well. And so both these systems, the one that I talked about yesterday and the one I'm going to discuss today, actually have a spintronics effect. That is, the spin is coupled to electronics, which is the motion of electrons. However, the difference yesterday, in yesterday's talk and today's, is that yesterday we're dealing with the real electron spin. Here in the beginning, though Avik later on brought in the presence of a real spin, but the spin that occurs initially in graphene is actually a pseudo-spin. The two states of the spin half operator are basically the occupation of the two sides of the AB lattice. Just to get started, you all know that there's a very nice review article by Castroneto et al. And our friend Bhaskaran, who is also in the conference, he has also written a review paper. And then I wrote two pedagogical articles in resonance and current science. Can graphene be used to teach quantum mechanics? The answer is in the affirmative. But most of the talk will be based on a paper that I wrote in 2021. The reference is given here. And it's actually also based on the theoretical treatment which is covered in a book that we wrote with Sanjay Puri, who is a colleague here in School of Physical Sciences. The work in 2021 was extended by Brishti Ghosh, who is in the audience, I think, here. And she is in IIT Bhubaneswar, worked with a former SNBO student, Malay Bandyopadhyay, who is the faculty of IIT Bhubaneswar. All right. So all this has been discussed by Ovik, but let me just put it in my way. It's fascinating to see that starting from the structure of graphene, the hexagonal lattice structure, the honeycomb lattice, they all occur due to the quantum chemistry of a single carbon atom. You all know from your chemistry lectures that carbon has 6 electrons, of which 2 are at the core, the 6 valence electrons, but 2 are in the core, and then you're left with 4 valence electrons. That's what you have to worry about. And then, now you have to accommodate these 4, and you would think that the first 2 will go into the 2s state, and the other 2 will go to the 2p state, but where 2 stands for n equal to 1, 2, etc., the eigenvalues. And however, there is something called promotion, which is talked about in Atkins' book on physical chemistry, that because of Coulomb effect, one of the 2s electrons actually goes into the p level and becomes a 2pz electron, whereas the 2px and 2py electrons hybridize with the one in the 2s state to give you this butterfly structure, which is here at the end. So this slide gives you that, and Ovik has already talked about it. So you get this petal structure, and the figure A is the 3 sp2 orbitals, and figure B is the unhybridized p orbital, and it is this sp2 hybridized butterfly structure is what gives rise to the graphene lattice structure. That is amazing that when you bring carbon atoms together, there is hand holding between these petals, which is shown in the next slide, whereas the two pz electrons in a half-filled state, it contributes to all our solid state properties, heat capacities, transport, conductivity, everything. So that's a fascinating thing of graphene. So again, this is a repetition of what I said, and it's actually a textbook quantum mechanics problem because you can now do a tight binding model, and this is a picture at the top where you have this hexagonal lattice. There are two interpenetrating triangular lattices. You have the green atoms and the red atoms. To do a tight binding approximation. Now, I'm a poor theorist. Avik is an experimentalist, so he used the second quantized notation, but I'll use the simple tight binding Hamiltonian to get to this dispersion relations. And it turns out that you have this half filling, and you have the green to the blue label thing, which is the valence band, and the green label thing is the conduction band, and then they meet at the so-called Dirac point, and you can experimentally put your Fermi level also at the Dirac point, and you have all these aspects of the spintonic effect of the Berry phase, which I will not go into. Amit and Agarwal and Avik Bir have worked on it, that because you have 2 degrees of freedom, sigma dotted with p, where one is a fast variable like sigma, and the p is supposed to be a slower variable, it's an adiabatic variable, and so if you go around the Dirac point without touching the Dirac point, you get into this Berry phase aspect. But this is not something that will occur in our talk. And you also have in the K space, K and the K prime band, which was shown by Avik. There are actually 6 of them, but these 2 are the ones that will occupy our attention. So Avik Bid had already shown you the Hamiltonian. After you do this band, the tight binding model, and then make an approximation, we go near the Dirac point, and then look at the lower order terms in K vector, what you end up is this fascinating Hamiltonian called the so-called Dirac Hamiltonian. It's called Dirac Hamiltonian because it's linear in the momentum variable, just like in special theory of relativity, unlike classical mechanics where you have quadratic energy in terms of momentum. But this linearity gives rise to all kinds of effects which are like the relativistic effects, but these is something that you can realize in the laboratory. You don't have to go to high energy accelerators or in outer space to do this, because it turns out that what appears as a prefactor, as Avik pointed out, is not the speed of light, but the Fermi velocity, which is 1/300 of the speed of light. So now you can easily write it down in terms of, by the way, I have already emphasized that sigma is not a real spin here. Sigma is a pseudo spin, Pauli spin operator, where the sigma z plus and minus 1 represent the 2 occupation probabilities for the lattice sites A and B, the blue and the green and the red, the pink in the picture earlier. And now you can write sigma. And so this is in 2 dimension. The K vector is in 2 dimension because you're working in a 2-dimensional graphene lattice. And then you can write down as sigma x kx, sigma y ky, and then write in terms of sigma plus and sigma minus. And you can actually diagram of the position operator. And when you work out the rate of change of the position operator with regard to this Hamiltonian through the Heisenberg equation of motion, writing in a commutator of this, x and p do not commute, and as a result, here's a fascinating thing also, the current density is now written completely in terms of, if you apply the electric field along the x direction, the current density is written completely in terms of the x component of the pseudo-spin operator sigma, and the prefactors are here. There's this print here, alpha, and these are the eigenstates of these 2 state systems, with the conduction band's eigenstates and the valence band. And so in terms of that, you can rewrite your current density operator, which is at the top. Somehow, yeah. So in terms of, we will introduce in the, in relation to the conduction band state ck ket vector and the valence band state k vector, we'll introduce what is called a depopulation operator. This is in analogy with nuclear magnetic resonance, where depopulation is what is associated with spin lattice relaxation, the T1 processes that you'll find in the nuclear magnetic resonance. And so, and then there's a dephasing operator also. So you think of a two-level system, and depopulation is basically transitions from one level to the other, which is caused mostly by phonons in the nuclear magnetic resonance and also here. And dephasing will be the spin-spin relaxation, which will modulate the excited and the ground level. And so now that can be introduced in terms of this kind of a dephasing operator. They're basically like, if you think in terms of sigma z and sigma x, sigma y, this is like sigma z and this is like sigma y. And the subsystem Hamiltonian is now diagonalized in terms of this depopulation operator, and this is your subsystem Dirac Hamiltonian. All right. So how do you talk about dissipation? Now, here I depart from Agarwal and company. They used a phenomenological rate equation approach to calculate the rate of relaxation of these various states. But that kind of misses out certain coherence factors, because the rate equation does not take cognizance of the non-off diagonal elements of the density operator. So we like to circumvent that issue, but reconnect with Agarwal and company later on. So here is a open quantum system approach. Those of you who were there in yesterday's lecture, I already introduced that. So you have a subsystem Hamiltonian, then you have an interaction term, which will couple to the so-called heat bath, and that coupling will occur through both the depopulation operator pi k and the dephasing operator yk, and the corresponding displacement operators for the bath system, which I denote by xe, e standing for electron relaxational effects, and xp the phonon effects. And so for you model xe and both xc and xp in terms of bosonic kind of excitations for the external bath. This is following Leggett and company, or in chemistry literature. I attended a conference long ago in Germany, where every time they'll talk about Caldera and Leggett, some chemists will get up and say, no, this is Swansig. So basically, Swansig actually did this work earlier, and also Ford and company. But anyway, so now one may ask the question that for electronic bath, why do you use a bosonic excitation? This was shown by Sudeep Chakravarti and a student of his back in 1985, that when you look at electron hole-like excitations across the Dirac point, you're going from the conduction band to the valence band, these low-lying excitations, you have electron hole excitations, and they behave actually like bosons with a given spectral density for the heat bath, which I'll indicate. The spectral density for the heat bath will differentiate between whether you're looking at spin-spin or electronic bath effects, or spin lattice or the phononic bath effects. All right. And for both these oscillations in and the oscillator bath system, you use a harmonic oscillator model as given in equation number 10. Okay. So here is your full Hamiltonian. You have a subsystem Hamiltonian, which you have diagonalized it in terms of the pi k operators. But you also have the effect of the electric field, which in a Kubo formula you treat in a linear response theory. However, the electric field is pretty large, there's something called, both Agarwal and company and we were induced by a FISREV letter by Mishchenko some years ago before Agarwal's paper. And so there's something called Mishchenko parameter, which is proportional to the Fermi velocity times the electric field divided by the frequency, and also square root of the two rates, which did not occur in Mishchenko's paper, but here the gamma p and the gamma e. The gamma p is a spin phonon relaxation rate, and gamma e is a spin relaxation rate. And so we are working in a large value of the Mishchenko parameter. And so we have to treat the effect of the externally applied electric field exactly. Now, when the electric field is time dependent, you know from your studies from Jackson's book that your vector potential also becomes time dependent, and the sigma dot k is like sigma dot p, so p has to be replaced by p minus ea over c, the way a is the vector potential. Now is time dependent, which you calculate from the electric field that you applied, and the net result is that you have a coupling between when you write down sigma dot p as sigma dot p minus ea over c, you get a coupling between sigma dot a, and so that's what this coupling term is. So this has to be then part of your subsystem Hamiltonian, then you have an interaction term and a heat bath term, and this is your open quantum system approach of dissipative quantum mechanics, which is again a part of non-equilibrium statistical mechanics in the quantum domain. So what you do is, unlike the rate equation approach, you write down the quantum Liouville equation for the density operator, which is a commutator between the whole Hamiltonian and rho of t, and from that you get an effective rho prime dependence. And how do you get the effective rho prime? What you do is something that you do normally in quantum optics. See, you're now going to write down a master equation for the density operator, which is already there in equation 17. This is a different name it has got, Lindblad, etc. But this is what is called the convolutionless master equation, which occurs in the book with Sanjay Puri that we wrote from here. And so what you do is a rotating wave approximation, because you see you're applying an electric field with a certain frequency. The subsystem Hamiltonian has its own characteristic frequencies. Those terms which are not resonant terms with the external frequency, they will die out very rapidly. So you only keep those which are in resonance. This is called the rotating wave approximation, very familiar in quantum optics literature, and that's what you do to write the master equation. The chairman is giving me a signal, so I'll now go to the results. And so it turns out that, and this rate equation, in contrast to the rate equation approach, you can actually now get the rates as a function of time. This is the so-called non-Markovian limit. You will get the Markovian limit only when you take the time t going to infinity. And what occurs in the integrand is a spectral density function. The cotangent hyperbolic function is a characteristic of the Bose factor, the Bose-Einstein, because of Bose-Einstein statistics for the Bath oscillators. And for the case of the electronic excitations, you use so-called ohmic dissipation, which is a frequency-dependent function with linear in omega, with a cutoff in omega c. So all these parameters will now go into the rate theory, and this is where Brishti Ghosh has done, who's in the audience, has done more detailed calculations. So here are some plots. They already appeared in our paper, and they are in agreement with this experimental paper by Jiang in nanotechnology, Jiang et al. So this is the variation of dimensionless spin relaxation rate at various temperatures. Now the interesting part is that at low temperature, like 30 degree Kelvin, the green dashed lines, you can see the rate actually first increases and then decreases. So this is the so-called non-Markovian regime, which is also there in the other case of the phonon-induced relaxation, where the spectral density has a different form. It's an omega q form, the so-called Debye form. And again, you see this kind of jump in the rate, which is not there in the usual treatments of the problem. And so now the question is, can this regime be probed experimentally? We have not seen, we'll try to induce a week to maybe probe this regime where you see non-Markovian effects in your relaxation rates. So I guess I will stop here so that I am on time, I think, right, Mr. Chairman?
Yeah, 7 minutes to 30 minutes. You have 7 minutes to 30 minutes.
I have 7 minutes to 30 minutes, so maybe I can then stop here to invite questions and criticisms, especially from Amit Agarwal.
Okay, let's thank Professor Dr. Gupta for that talk. Questions from the audience, please.
Amit and Didi are my worst critics, so maybe.
Private, yeah.
Is that a criticism? But I thank Didi because he's staying through my lectures and he's going to leave soon, I think. Yeah. Well, he's going to leave in the afternoon, right? In the evening, yeah, right. Okay. Any other question from maybe the students? If I have been a little technical.
So maybe for younger colleagues, what are the generalizations of this other problems that younger colleagues can take up with?
You mean not in graphene?
Either in graphene or other systems?
Well, in the Rajba system on Shubhankar and company, we already did some work to analyze their data on Shubnikov-Dahas oscillations in planar Hall effect and anisotropic magnetoresistance. There are many other applications which I can talk to you privately because they are very technical. And Shomik Gupta and I have done some work. Shomik Gupta is in TIFR now. And so we actually are writing a review article also. Maybe over the tea break I'll talk to you about it. They're a bit technical theory-based things, yeah.
Okay, any other questions? Okay, so if not, maybe I thank Professor Dutta Gupta for the talk.